In this video, we're going to devise a way to analyze small deviations from the bias point that is called small signal modeling. We're going to use small signal models a lot in this semester, so stay sharp during the video. We start by assuming that our resistor diode circuit has an input that consists of a big fixed component plus a small variation on top of it. We call the combination of these two signals the total signal. We call the large fixed component the large signal, and we call the small variation the small signal. There's a notation convention that's associated with this type of modeling, where total signal variables are denoted with a lowercase letter and an uppercase subscript, so like this VD. Large signal variables are denoted with an uppercase letter and an uppercase subscript, so like that VN. And small signal variables are denoted with a lowercase letter and a lowercase subscript, VN. And the total signal is equal to the large signal plus the small signal. It's common to draw small signals as AC sources, like I've done in this circuit, but the math we're going to pursue in this slide doesn't actually require the small signal to be varying. You can have small DC variations that are effectively modeled by small signal modeling. I mention this because we're going to use some models later that do require sources to be time varying, and it's important to keep track of which assumptions are associated with which models. A picture of the diode's experience of this model is shown in the curve in the upper left. Our input looks like a small variation with a DC offset, so here's the DC offset, small variation back and forth. And that will cause the current to move up and down as we change our operating point along this diode curve. Notice that I've used total signal labels for both the VD and ID here, and that I've expressed ID as some function of VD, that function being this exponential. The big trick we're using with small signal modeling is combining superposition and Taylor series expansions. This picture over here shows the Taylor part of that trick. Here we say that the total output signal, little I big D, is equal to the sum of a large signal, ID, which is the first term of Taylor series, and a small signal ID, which is the second term of Taylor series. The first term of a Taylor series is calculated by evaluating the sort of Taylor function at the operating point, at the x that you're evaluating at, which in this case is the large signal voltage applied to the circuit. And so together, this large signal VD and ID describe the operating point of the circuit. They tell you what your bias point is. The large signal representation is added to a linear approximation of the variation away from the operating point. So we need to calculate the slope of our diode curve at the operating point, which we represent by the derivative of ID with respect to VD, evaluated at large signal VD. And then we multiply that slope by our small deviation VD. There are a few things to notice about this model. First, this model only deals with deviations from the bias point. Said again, small signal models only tell you about small deviations, not about absolute values. Foreshadowing a bit, that means we're going to shut off sources in our small signal model circuits because sources never have small deviations in their value. Second, this derivative tells us the slope of the diode curve at our operating point. But we have an equation for ID that we're not using on this slide. So that suggests we might be able to come up with a cute expression for this slope, and we're going to do that on the next slide. Third, dVd is a conductance. It would have units of amps per volt. And you'll notice we get a current by multiplying it by a voltage. but we're mostly used to dealing with resistances in our circuits. So when I wrote the vertical variation of ID here, I represented it as 1 over RD instead of just some other constant representing that derivative. Where RD here is something called the differential resistance. And that differential resistance becomes the small signal model for our diode. We replace diodes with little resistors in our small signal model. And RD is going to vary as we change VD, because we are evaluating a derivative with respect to VD to calculate it. So RD is the inverse of the slope at every point on the diode curve. We can see that being applied to a circuit in the pictures below. So we're turning this mathematical representation into a circuit representation. In the circuit representation, we're using superposition to add a large signal circuit together with a small signal circuit. And the small signal circuit only captures variations away from the large signal bias point. Our large signal circuit ignores the small signal input source. It's no longer here, and that's because it's small, and the large signal circuit is just trying to capture sort of big details. It's small compared to Vn, so we can ignore it. We often solve large signal circuits containing diodes using the switch voltage source model, and I've done so here. The small signal circuit zeroes out the large signal Vin, because the large signal Vin will never change its value. Voltage sources are always fixed at a constant value, and so we can zero them out in circuits that only care about change. It has 0 small deviations. Also, the diode in the small signal model has been replaced by this differential resistance in order to indicate that if we change VD a little bit, we're modeling changes in ID linearly, and the amount they change is given by this resistance value, where this resistance is the same as the coefficient here, which is the same as this slope. So we could apply this model to figure out variations in the small signal VD as a result of the small signal Vn, and we'd find it's just given by a simple voltage divider. So if we had a value for RD, that would be a really quick calculation and a big win compared to not being able to figure out changes on a diode at all previously. Which, by the way, is something else that the switch voltage source model would have omitted. So, in order to do that, we have to calculate a value for our differential resistance. We can substitute the diode equation in for ID in the derivative that we take to find our differential resistance. So we're making our small signal model of the diode by taking a derivative of the diode equation, because the small signal model represents the first term of Taylor expansion. Then we evaluate that derivative, which eliminates the -1 term, it's a constant, and brings a 1 over n phi th out in front from the exponential. And this would be a usable expression, but it's kind of clunky. It would be hard to calculate this in lab because I can't do exponentials in my head. However, we can notice that this term here is about the same as ID. The only thing we're missing, as our large signal ID, the only thing we're missing is the -1. You know, if VD is bigger than phi th, that -1 is kind of small. So we can approximate this as our large signal ID and rearrange our algebra slightly to find that our differential resistance is equal to n phi th over ID, which is a very handy way to calculate differential resistance. I want to call attention to this substitution step where we called this approximately large signal ID. First, I want to note that we're using the large signal VD in this expression, in the derivative we're taking, because we evaluate our derivative at a large signal value of VD. And then second, I want to point out that this substitution is extremely common when you're making small signal models. It's a way of simplifying the model significantly. And so when you are making small signal models, you should look for the opportunity to do it. Asking you to make a small signal model for a weird device on a test is a classic curveball question. And so this substitution is a place where a lot of people miss a few points, and I want you to be prepared for it. Right. Finally, the art on the right here is just a reminder that we're representing the full nonlinear diode as a large signal, which is a constant model, and I've just represented that as V on the switch voltage source, plus a small signal, a linear approximation to the diode's behavior that tells you how the current changes with voltage, and we've chosen to represent that linear approximation as a resistor. So, in summary, you can use superposition and Taylor series to make linearized circuits that capture small deviations from a bias point. The circuit representing the first Taylor term is called a small signal model, and you find it by taking derivatives, often of device equations. And the small signal model for a diode is a resistor, and it's called the differential resistance. And the equation for it appears down here.